right, so we're on 10.2, and we need to do some definitions first. Let's draw a circle, and we're going to put a point P in the middle, and this is going to be A, this is going to be B. We're going to put some random point out over here that we're going to kind of call C. And so for this drawing here, we call this a central angle. Try to write that a little clearer. Central angle. This is referred to as a minor arc. Smaller arc that runs from A to B. This bigger arc that runs around this way is called a major arc. And so, just to define some of these, I'll do it over here. A central angle has its vertex at the center. We'll use a little abbreviation for circle. AB, arc AB, so it's like AB with a little, what is that?
Rainbow.
A rainbow, a little rainbow, so like rainbow of one color over the AB. That is what we call a minor arc. And then I could designate arc ACB. That's why we put that extra point out there, so we would know. We couldn't just say AB because we'd think, well, is it this way or is it this way, right? So we put that point C out there so that we could say arc ACB is a major arc. And then, so make sure you know that definition, this definition, this definition, and then finally, the measure of angle APB equals the measure of arc AB. So the measure, if we talk about the measure of this arc, it's the same as the measure of this angle right here. And if we want to know the measure of angle ACB, then that's going to be 360 degrees minus the measure of AB. That should be kind of obvious to us. Does everybody understand that? The circle as a whole is 360 degrees, and whatever the measure of AB subtracted from 360 is what the measure of angle ACB has to be. Any questions about those definitions? Somebody's jamming.
Is the circle just one continuous arc?
Who is that? I'd like to teach, but I can't quit dancing, you know?
I like that ringtone.
All right. So find the measure of each arc of circle R. So we've got, why I drew that so little. We've got this circle here. We put an R in the middle. We'll do N, P across here, R here, N, P, and then they tell us that this is 80 degrees. And we label this M down here. So they want us to find the measure of arc MN. And so, what's the measure of arc MN?
80 degrees.
It's 80 degrees. It's whatever the measure of that angle is there, right? The measure of the arc is the same as the measure of the angle that runs of that central angle that matches that arc. What about the measure of arc MPN? So everything around here,
280.
280. Is that 360 minus 80?
Right.
Then you're right. Good job. Nice job, Cal. 360 degrees minus 80 degrees, which is the measure of arc MN, so he's right. It's 280 degrees. Did I hear you say the same thing, David?
I said it was going to be 360 minus 80 degrees.
Okay, good. Excellent. And then finally, PMN, arc PMN. So arc PMN. How do I know the measure of arc PMN?
180?
Well,
180.
we don't necessarily know that for a fact.
We're kind of judging by the way that it looks like it's drawn, right? It looks like that is a line that goes from N to P, and since it crosses through the center point R, then it's safe to assume, like you said, that this is a diameter here. So that cuts our circle in half. So like you said, that's got to be half of the measurement around the entire circle, which would be 180. All right. Any questions about that? So if you see a line that goes through the center point, then you know that that's a diameter. We'll cut it in half. No questions? All right, let's introduce you to postulate 26, which is the arc addition postulate. And that says the measure of arc ABC. If we have arc ABC, then that total measurement is going to be the measurement of arc AB plus the measurement of arc BC, right? So if we had, basically, if we were to label this guy A, B, C, then whatever the measurement is of AB plus the measurement of BC would give you the total measurement of ABC. So we can do one example. Well, we'll just draw one circle. And do example 2. So where it says, I've got a center point, I've got G up here, I've got H right here. This is 40 degrees. Got a measurement down here, which it says is 80 degrees. That's E. And a line over here. So this is 110 degrees, and this is F. And it asks us, what is GE? So what's the measure of arc GE? Joshua. 120, and you got that by adding together the measure of arc GH with the measure of arc HE, right?
Mm-hmm.
So 120. Excellent. GEF. just going to do the same thing, but add the 110 in there, right? So the measurement of arc GEF is going to be 40 plus 80 plus 110. So it's going to be the 120 plus another 110, which is 230, sorry. 230 degrees. I was about to write my name on the board. Give myself some credit. And then the last one is the measurement of GF. How do we figure out the measurement of GF?
Subtract, what was like the 230 from
Yep.
360.
From 360, right? So measurement of GF, since we've already found GEF, it's going to be 360 minus the 230, which is what GEF was, and so that's going to equal 130. Good. That's simple and straightforward enough, right? You guys would have no problem taking a quiz over that, right? Easy enough. So let's move on to, let me see if there's anything, identifying congruent arcs. They just said, are the arcs congruent? So if you look at the book, for arc AB and arc DC, are they congruent? They're both 45 degrees, right? So what does congruent angles mean? If I say angle A is congruent with angle B, what does that mean? It means that the measure of angle A is equal to the measure of angle B, right? So if I'm determining if two angles are congruent, I'm determining, do those angles have the same measurement? And clearly, arc AB and arc DC have the same measurement. They're both 45 degrees, so they would be congruent arcs, okay? So just like, since this applies to angles, if you have arc AB and it's congruent to arc, whatever, arc CD, then that means that the measure of arc AB has to be equal to the measure of arc CD, right? So that's what makes them congruent. So for these two problems, for these for A, B, and C here, this is angles. Does everybody have their book? So I don't have to write it on the board. You see what we're talking about? For those, would PQ and RS, those arcs be congruent? Yeah, they have the same measurements, right? What about for C, when we're looking at XY and WZ, those arcs? So this has to do with one final caveat with congruent arcs. They have the same measurement and they are part of the same circle or of congruent circles. All right. So this is only true that they're congruent if arc AB and arc CD are on the same circle or on congruent circles. All right. So the answer actually for this one is that they would not be congruent. Even though we would say degree-wise that their measurements are the same, they're not congruent because they're not on the same circle or congruent circle. All right, so that's just kind of one caveat that we don't really have with this idea of angles. It makes arcs a little bit different. But it does kind of make sense if you think about an arc. It's the degree measurement as it correlates to that distance between the points, right? And clearly, since these circles aren't the same circle or congruent circles, then the distance between those 2 points is not going to be the same. So just kind of keep that in mind as we're talking about congruent arcs. They have to be on congruent circles or on the same circle. And their measurements have to be the same. All right, let's list 3 more theorems up here. And work a few problems, bless you, related to these theorems. Theorem 10.4. And that says that arc AB is congruent with arc BC if and only if AB, the distance AB is congruent, the line segment AB, I'm sorry, is congruent with line segment BC. So we need to draw a picture to make sense of this. So what it means is we have something like this, and we've got B, A, C, all right, so in order for arc AB from here to be congruent with arc BC, this distance here, that is only true if these two distances, line segments drawn from AB, from A to B and from B to C, are also congruent with one another. Okay? Does that make sense? Does that theorem make sense in light of this drawing here? So we have to use that in a proof, or just be able to do a problem that's got some unknown values. So if we're told, I could give you a problem that tells you that arc AB and BC are congruent to one another, and then maybe give you some x's here where the length of those line segments are, and say solve for the value of x. Yes?
You put 10.4 and 10.4.
I didn't I? That's a problem. You're gonna call me out on that, aren't you? In front of the whole class. Okay. I'll just have to erase your name and fix the problem. I would never do that. All right. Thank you very much. 10.5. So this theorem says if the diameter of the circle is perpendicular to a chord, then it bisects the chord and its arc. In other words, DE is congruent with EF. I'm going to have to draw a picture for this too. DG, arc DG is congruent with arc GF. All right, let's draw that picture. Refresh our minds on what a chord is. I'll just leave that. Let's draw another one. So we've got something that looks like this. It looks like this. And we've got D, G, F, point E right here. This has to be congruent with that. We've got a center point here, which we're going to not label, and then we've got a point C over here. There. So, what is the chord in this drawing? You guys remember the definition of a chord? Yes, Ian.
DF.
DF is the chord, right? The chord is just a line segment that runs from one side of the circle to the other side of the circle. There is a special chord, which is the longest chord of the circle, which we call the what?
Diameter.
The diameter, right? So we've got Aiden, is that what you were going to say?
Yes.
He was shaking his head like crazy. I'm going to go ahead and give him I mean, I thought his head was going to fall off. It was just like, we need to give him some credit for that. But yeah, chord just runs from one side to the other. And so what we're saying is that if the diameter, which is in fact a chord right here, bisects another chord, I'm sorry, if it is perpendicular to another chord, then it bisects that chord and therefore makes two congruent line segments and also two congruent arcs. Okay? And then finally, theorem 10.6. And it says if one chord is, if one chord is a perpendicular bisector of another chord, then the first chord is a what? What do you guys think it's going to say? Don't leave the book. Based on what we just defined here, what do you think I'm going to write next? Diameter, right? So if one chord is a perpendicular bisector of another chord, then the first chord has got to be a diameter. I.e., in our drawing, CG is a diameter. Okay? All right, so let's look at some problems that will give us an opportunity to use these theorems. And the first one is pretty straightforward. It's exactly the type of thing that I said that I could ask you based on, excuse me, 10.4, theorem 10.4. Let's redraw it. So if I've got a circle, looks like this, and I've got B in the middle. Something looks like that. And then we've got this, and that. And we're told that these are the same length by having the little slash through the line segment there. And then we're told that this is 2x degrees and that this is x plus 40 degrees. And we're asked to find the value of x. So how would I find the value of x? And how is this theorem 10.4 going to help you do that? Camille.
Would you do 2x equals x plus 40 degrees?
That's right, because we know since these line segments here are congruent, then it means then that the measure of these arcs have to also be congruent, right? So 2x equals x plus 40. Now guys, make sure that you actually know this, because I get the distinct feeling sometimes whenever I'm looking at your quizzes or your tests that you'll just sort of, you see something with x in the problem and you're like, I'm either going to set them equal to one another, or I'm going to add them together and say they equal 180, or it's like you just kind of randomly pick something out. And this is sort of the default one. I'm going to set them equal to one another and solve for it, and maybe that'll be right? So make sure you understand this. If I write it on the board and you're like, I don't really understand why you did that, ask me so that I can walk through that. All right? Is everybody clear why we said these are equal to one another?
Yes.
It's just straight out of this theorem, right? All right, so then if we solve that, we just move our x over to the left side and x equals 40. It's actually very simple algebraically. Not much to that. Doesn't really have a good example of 10.5. So I guess I need to go ahead and give you theorem 10.7. Let's see. I mean, I guess there's a problem in the homework that says that basically has a drawing that sort of looks like this, and it's got this extra line that comes off right here, and we could label that A, whatever, A up here. So they've got a drawing that kind of looks like that, and they tell us that the length of this side is 40 degrees, and they tell us find the length of the arc that's in red. And so if I saw a drawing like this, and I'm trying to find this length x right here, what would that length x have to be? Eighty?
Because they're perpendicular, it bisects that arc in the chord that it's corresponding to, so they would be equal to each other.
It'd be what?
Equal to each other.
They'd be equal to one another, right? So it's just this right here. It's just this fact. Since we see that it bisects the chord, we know it bisects because these are both listed as being, those line length segments are listed as being equal to one another. So that means that it has to be also 40 degrees. So that one's pretty straightforward. And like I said, the way that we might make it more complicated is to do something like this, right? When we give x values, and then you have to do the algebra after you set the two of those equal. All right, any questions about that before I go over theorem 10.7? Trying to make sure I can really get through 10. The next section as well. So let's go and do 10.7. Theorem 10.7 is another one. Is just it just kind of tells you what if I can reuse this triangle maybe. So if we have a triangle that looks like this. Try drawing that again. It's like this. And this looks like this. And label that D, B, C, A. We've got a center point here, which is E. So we've got a right triangle here and a right triangle there. And we're going to label this point G. And we'll label this point F. And so what theorem 10.7 says is that two chords, just erase this one, two chords are congruent if and only if they are equidistant from the center. In other words, in our drawing, line segment AB is congruent with line segment CD. If and only if line segment EF is congruent with line segment EG. All right, so we've given a triangle like this, and we're told that AB equals 8. That was terrible. And B equals 8. And DE equals 8. And CD equals 5. And they want us to find CF. What is that distance equal? All right. So how is theorem 10.7 going to help us answer that question? Theorem 10.7 is about two chords being congruent. Do we have two chords that are congruent? I'm seeing some head shaking no, but I'm also seeing some head shaking yes.
A, B, and D, E.
What?
A, B, and D, E.
A, B, and D, E are both of those chords? What is a chord again? A chord is a line segment that runs from one point on the circle to the other side, right? To another point on the circle. So those are by definition chords, and does everybody see because of the measurement being 8 for both of those that those are congruent chords? Because what's the definition of congruency, right? A line segment AB is congruent with line segment DE if the measurement of AB is equal to the measurement of DE. That's what congruency means, right? So, Dave's right. These two are congruent with one another. So since we know we're dealing with congruent chords, then that means we know that line segments drawn from the center that are perpendicular to those chords have to be the same measurement, right? EF and EG has to be the same. Do you guys see that? Now, what is DG?
Is it 4? Is it a 3, 4, 5 triangle?
Yeah, so DG, AB and D are congruent chords. They are equidistant from the center. And CF is congruent with CG. So we've written that down. CG, we have to find DG first. And CG and DE, let's see, CG and DE are, CG bisects DE. How do we know that CG bisects DE?
Is it a 90 degree angle?
Yeah.
And it starts at the center.
Because it's a 90-degree angle that starts at the center, right? So if we could extend this on through, then what we actually have here is a diameter, right? That's intersecting that chord at 90 degrees. And so the reason that we know that it bisects it is because of theorem 10.5, right? So that tells us that that's bisected. And if it's bisected, then it tells us that the distance DG and GE are the same. Since we know the total distance of DE to be 8, then this has to be 4, and this has to be 4. Does that make sense to everybody? And so now, right, someone said, was that you, Jackson? We have a 3, 4, 5 triangle, right? If you don't remember the 3, 4, 5 triangle, then you could always use Pythagorean's theorem and just set this equal to x, right? And say x squared plus 4 squared equals 5 squared. And what you're going to come up with when you solve that is that x equals 3. So we're going to see that distance is 3. And since we were trying to find this distance CF, now we know that CF has got to be equal to 3 because it's the same length as that side. This length is the same length as this side here. Okay? So we had to use a couple of different theorems to figure that one out. But did I lose anybody in the thought process there as we were going through that problem? Now's the time to ask the question. I feel like some of you guys are kind of like me. It's like it's coffee time, right? Just a little bit of caffeine. No questions? All right. Well, I'm going to move on into the next section then. So let's go. Let's move on into section 3, and let's define an inscribed angle. So an inscribed angle looks like this. You've got a circle and you've got a point. You've got an arc that's created by an angle whose vertex is over here on the other side of the circle. Okay? I feel like I said triangle a minute ago. Did I say triangle? Did anybody hear me say triangle? I keep almost saying triangle, but I actually say it this time instead of circle. I'm meaning to say circle. So we have this is what we call an inscribed angle. All right, and this is over here is what we refer to as the intercepted arc. The arc that's created by the inscribed angle. And so what theorem 10.8 tells us is that and this is called this theorem is the measure of an inscribed angle. It tells us that if we were to label this, say we were to put a point right here in the center, and we were to create what do we call this angle that's created by the center, huh? I did find that last section. You guys remember? Yes, Aiden?
Center angle.
Huh?
Center angle.
It's a central angle. Remember? Close. It's similar to center. That's a central angle. So if we create a central angle from this point C, and we have labeled this point D and this point A and this point B, then this theorem says that the measure of angle ADB, so that's our inscribed angle, the measure of our inscribed angle is 1/2 the measure of arc AB, the intercepted arc. It's not supposed to be a line segment, that's supposed to be an arc. Or you can think of it as 1/2 the measure of angle C, right? Because that is the measure of arc AB, it's the measure of that central angle C. Okay? So whereas the measurement of this arc is the measure of the central angle, the measure of the arc is going to be 2 times the measure of the inscribed angle. Does everybody see that? If this is true here, if measure angle ADB is equal to 1/2 the measure of angle AB, then that means that 2 times the measure of angle ADB must equal the measure of arc AB. So arc AB is twice the size of the inscribed angle. Right, I'm just going to write these theorems down real quick and well, maybe I don't. Maybe I'll do an example first. So, I mean, this is just kind of a weird one. I'm just going to do one. It's just weird looking, right? But if I had a circle that looked like this, and I had these points ZX right here, and I was told that this was 115 degrees, and I asked you what would the measurement be of, this is y, what would the measurement be of arc xz, what would your answer be? Based on theorem 10.8, that means that the measure of angle XYZ, right, has got to equal 1/2 the measure of arc XZ. You guys see that? Or, like I said, I could write it and say that the measure of arc XZ has got to be equal to 2 times the measure of angle XYZ. So that's 2 times 115. So that equals 230 degrees. I feel like I need to just kind of sit down and let that sink into you guys. Wasn't getting much feedback on that one. Is it just so simple that you're like, why are you asking me this question? Or are you sleeping with your eyes open again? What's happening? You guys got it? You tracking with me? Yeah? Okay. It's so funny. It's like sometimes there's a lot of excitement in this class, and other times it's just like, maybe you're there, maybe you're not. I mean, when there's clapping and cheering and all, the guy next door is probably like, they must not be having class today. And it's just so quiet over there. Probably no one there. All right, what if we had theorem 10.9? What if we had, I wrote that down twice. Theorem 10.9 is 2 inscribed angles. So if 2 inscribed, and I'll spell it correctly in a second. If 2 inscribed angles intercept the same arc, the angles are congruent. In other words, let's draw this here. So we've got arc AB right here, arc AB. And so we say that we've got a point C over here, and we've got a point D over here. And so we've got an inscribed angle that goes from here to there. Right? Looks like that. And then we'll draw another inscribed angle from a different point over here. It goes to the same arc, right? Looks like that. And so what this theorem tells us is that angle C is congruent with angle D. And that should make sense to us based on what we know about the measurement of an inscribed angle. It's related to the measurement of the intercepted arc. So it would make sense that those are congruent with one another. Let's draw another. Go ahead and write down a couple of other theorems. But first let's draw a picture here. If I had a picture like this, so I've got a, it's not very nice looking. Try that one more time. So it should go over here. And that goes down there, that goes down there, that goes sort of like that. All right, I'm trying to draw a pentagon inside my circle. It says if all vertices of a polygon are inside a circle, the polygon is inscribed. Okay, so this is just how we define an inscribed polygon. It's inscribed in the circle. And the circle, another definition, is circumscribed about polygon. All right? So we need to define those terms before I give you these last two theorems so that you'll understand what the theorems mean. So theorem 10.10 says that if a right triangle is inscribed, why do I keep doing that? The right triangle is inscribed. So in other words, we have circle here, got a right triangle inscribed in our circle. We'll label that ABC. So if a right triangle is inscribed, then the hypotenuse is the diameter. So the hypotenuse for an inscribed right triangle will always go through the center of the triangle. All right? And since by definition, with it being inscribed, that means that all of its vertices lie on the circle, then it will always be, the hypotenuse will always be a diameter. Conversely, if one side of an inscribed triangle is a diameter, then we know that triangle is a right triangle. The opposite, the angle opposite is a right angle. So to say that kind of succinctly, we could say, so angle B is a right angle if and only if AC is a diameter. Does that make sense? Just kind of spelling that out, right? I could give you a circle, and if you could prove that one of the sides, I could give you a triangle, an inscribed triangle, and if you could prove that one of the sides went through the diameter, then you would know that triangle was a right triangle, and you'd know which angle was the right angle. And then finally, theorem 10.11 has to do not with an inscribed triangle, but an inscribed quadrilateral. A quadrilateral is inscribed in a circle if and only if its opposite angles are supplementary. So, in other words, let me draw one here. If I had a circle that looked like this, and we had a quadrilateral that looked like this, and we labeled it E, F, G, D with center C. This theorem says that the measurement of angle D plus the measurement of angle F equals 180 degrees. And the measurement of angle E plus the measurement of angle G equals 180 degrees. So each opposite angle in that inscribed quadrilateral, when you add those angles, those angles are supplementary. So when you add them together, you get 180 degrees. All right. So let's do a couple of quick problems to use those theorems, and then I'll let you go. So I think that's probably the easiest way to grasp the theorem is just to do an example. So we have this, and we have this right here, and we're given that this angle is 2x degrees, and they said find the value of the variable. So based on that drawing there, what is x? How would I find the value of x? Are you guys still writing? Don't look at this then. Pay no attention to that drawing until everybody's done writing. All right, you guys ready to focus on this now? You see it? Based on what we know from theorem 10.10, what does angle 2x have to be equal to?
90.
It has to be 90 degrees, right? Because it has this, one of the sides of this triangle here go through the center. So that means it has to be a diameter. So it means that this angle here has to be 90 degrees. So 2x has to equal 90, and so x has to equal 40. X has to equal 45, right? Super simple. And then what if I had, if I had a triangle, triangle, there it goes again. If I had a circle, it looks like this. And we had some distances that were, some angles that were like Z. This is 120, and this is Y, and this is 80 degrees. What does the value of Z have to be?
80. Wait, no.
What does 1011 say?
100.
It has to be 100 because theorem 1011 says that Z plus 80 has got to equal 180. It says that this angle and this angle, they're supplementary. So when you add them together, you get 180. So Z has to equal 100. And then Y has to equal 80, right? Y equals 80 because 80 plus 120 right here, Y has to equal 60 because Y plus 120 has got to equal 180. 60 plus 120 is 180. Okay? Any questions about any of those theorems? I want to make sure that you can do one that's a little more complicated, and that's what example 6 is. So I'm just going to set this up for you and just see if anybody has any questions about it. It's just using the same thing, the exact same method that we just used, but there's a little more algebra involved, right? So if we had something that looked like 2y here, 2y degrees there, and then 3y degrees here, and then 5x degrees here, and 3x degrees there, and they asked us to find the measure of each angle. Again, this is one of those problems where you got to make sure that you pay attention to what the problem asks for, right? Find measure of each angle. So, based on the way this is drawn, give me some equations that I could set up in order to find the value of x and y. Is somebody not on the board? Can someone not on the board tell me how to do it? Mary.
So, using theorem 10.11,
Yep.
you do like 2y plus 5x equals 180.
Okay. Good.
And 3x plus 3y equals 180. Or you could do 2y plus 5x equals 3x plus 3y.
Yep.
And that would, you could,
Both of those, but we still couldn't solve that, right? We're going to have something like this in order to find the value of both variables. So if she's right, since we know both of these equal 180, we could say that they're equal to one another. But that's still, even if we solve that, we're going to have x's and y's and just one equation. And in order to solve for two variables, you got to have two equations, right? So this is our two equations that we could use for those two variables. And so how would I use these equations to solve for these variables? I want to make sure you guys remember how to do that. You could use, there's two options, elimination or substitution, right? So with elimination, you basically have to multiply through by something that will, you can then like add them together and one of the variables goes away. So we could, for example, multiply this top one times 3 and this bottom one times -2. And then when we add them together, whoops, wait a minute. Let me write these in the correct order here. 5x and 2y. Let me do my x's. There we go. So that still works out. So if I did something like that, I would have 15x plus 6y equals, wow. What is it, Grace? What's 450 plus 90? 540? Is that right? And thank you, Grace. 6x minus 9y equals negative 360, right? So why did that not work out? What did I do wrong? I did this wrong right here.
How did you get
Negative 6, sorry. There we go. So then when we add those together, 6, this is 9x equals, oh, whatever, 180? Is that right?
huh.
Is that right? And x equals 20? Did I do that right?
Looks like.
Okay. So does everybody remember how to do this? Elimination or substitution, right? This is something that's kind of blast from the past, so you still got to remember how to do that in order to solve those variables. So then you can get x equals 20, and we can take that 20 and we can plug it back in any of these guys to figure out that y is equal to 40. But then remember, when you're done finding x and y, go back and read the instructions to your problem again and make sure that you're giving me what the problem asked for, because the problem didn't ask for the values of x and y, it asked for the values of each of the angles, right? So that would mean then we have to say that this angle here is equal to 80 degrees, this angle here is equal to 120 degrees, this angle here is equal to 60 degrees, and this angle down here is equal to 100 degrees, all right? So that would be the final answer to the problem. All right, you guys have a good day and enjoy your spring break.